So this is the third and final video on rates of reactions, which again is a paper 2 topic, and this video is going to focus on collision theory. Below I've written out a chemical reaction between hydrogen and oxygen to form water. Hydrogen and oxygen are my reactants. They will react together to form the product water. In order for hydrogen and oxygen to actually react, they need to physically collide. Not only do they need to collide with energy. If they collide and they don't have much energy, they will simply just bounce back off each other. But if they collide with sufficient energy, then they are able to react and form H2O. In this topic, we've been looking at rates of reaction, so the speed of a chemical reaction. If you want to increase the rate, if you want to increase the speed, then you need these collisions to be taking place more frequently. Anything you do to increase the frequency of these collisions is going to speed up your overall reaction. And in this video, we're going to look at the different things that you can do to increase the frequency of these collisions and therefore increase the reaction. The first thing we're going to look at is to do with surface area. So in the reaction I've got here, I've got carbon, which is a solid, reacting with oxygen, which is a gas, to form the gas CO2. If I want to increase the rate of the reaction, and by rate of the reaction I mean speed, I need carbon and oxygen to collide more frequently. One way I can do this is I can increase the surface area of my piece of carbon. Below, I've got two different examples. I've got carbon, where I've just got a large lump of carbon, and then I've got carbon where I've broken it down into small little pieces. When you've got a large lump of carbon, you can see that I can only get a few oxygen molecules around the piece of carbon. In total, I've drawn 6. When I take that same size piece of carbon and break it up into lots of small pieces, I can fit way more oxygen molecules around carbon. If there are more oxygen molecules around carbon, then I'm going to get more frequent collisions, and that's going to increase my rate of reaction. So to describe this, I would say I have increased the surface area. So this is my large piece, this is my small piece, but the small pieces have a larger surface area. Larger surface area. So by taking a large piece and breaking it into small pieces, you've got a larger surface area. So if you increase the surface area, you increase the frequency of collisions because more molecules can get around the carbon, and therefore you're increasing the rate. Surface area, increasing the surface area is only going to apply to solids. So in this case, I could increase the surface area of carbon by cutting it down into small pieces that increase the frequency of collisions and thus increase the rate of my reaction. Make sure you are saying frequency of collisions and not collisions. Even if you've got a large piece of carbon, you will overall have the same number of total collisions. It's just that in this case, the collisions can happen faster. So you're increasing the frequency of them, how often they're occurring. You're not increasing the overall number. Another thing that you can do is change the concentration. So when I'm talking about concentration, I am typically talking about solutions. So with surface area, I was looking at solids. With concentration, I'm talking about solutions. For an example, an acid would be in solution. And if we look at the two drawings that I have below, the drawing on the left has a lot less particles than the drawing on the right. If you have increased the concentration and if you've got more particles, then you are more likely to have collisions. So by increasing the concentration, I'm going to increase the frequency of collisions, and therefore I'm going to increase the rate. This is particularly applicable to solutions such as acids. If you increase the concentration of an acid, if you put more particles in there, then you're increasing the frequency of those collisions. That will therefore increase the rate. So that was surface area for solids. We have concentration for solutions. For gases, we're going to be looking at pressure. So here in my diagrams, I've got an example of low pressure, and I've got an example of high pressure. And you can see that under high pressure, the gas particles have less room. If they've got less room to move around, they are more likely to collide. So by by increasing the pressure, by going from low to high, I'm creating less space, and if there's less space, there's going to be more frequent collisions. It's like if you had a number of people in a room and then you move them into a smaller room, they're more likely to collide in that smaller room than when they had lots of space and could avoid each other. Particles are the same. So increase the pressure, you're going to then decrease the space. If you decrease the space, you will have more frequent collisions. Again, I'm not saying more collisions, I'm saying more frequent collisions. The last factor we need to look at is going to be temperature. And temperature has two effects. The first effect that temperature has that it will increase the speed of the particles. Increasing the temperature gives them more energy. If they've got more energy, they can move quicker. If those particles are moving quicker, you're going to get, again, more frequent collisions. Okay? So if you're all standing up in a room and you're walking slowly around it, you'd avoid each other. If you start to run around it, you're more likely to collide. Same with particles. Increase the temperature, they move quicker, they're going to collide more frequently. If they're colliding more frequently, you've increased the rate of the reaction. Temperature has another effect though. At the start, I mentioned that it wasn't enough for particles just to collide, they had to collide with a sufficient amount of energy. If they don't have much energy when they collide, they'll just bounce off each other, but if they have enough energy, when they collide, they can actually react. Because increasing the temperature gives particles more energy, more particles will then have the necessary energy to react. And this necessary energy, the energy that's needed to react, is called the activation energy. So it's the minimum amount of energy that reactants need to react. And by increasing the temperature, more particles will have the activation energy and more particles will be able to react. So increase the temperature, you're going to increase the energy of the particles. And if you're increasing the amount of energy they have, then more particles will have the required activation energy. Okay, so that's surface area for solids, concentration for solutions, pressure for gases, and then temperature you can say for every reaction. Okay, it doesn't matter if you're dealing with solids or liquids or gases. If you increase the temperature, you're giving them more energy, more frequent collisions, and more of them will have the required activation energy. There is one other thing that can increase the rate of the reaction, and that is a catalyst. And catalysts are substances that increase the rate of the reaction without being used up. For all of the other examples, we've seen that they increase the frequency of collisions, but catalysts don't do that. Instead, what catalysts do is they lower the activation energy required for a reaction. So if we look here at this diagram, I've got my reactants on the left-hand side and my products on the right. In order for the reactants to become products, they need to have a certain amount of energy. And I've just assigned the value 500 joules, just kind of arbitrarily. My reactants need to have 500 joules of energy in order to be able to react. What a catalyst will do is it will lower that requirement. Instead of the particles needing 500 joules to react, you now only need 250 joules to react. Because I've lowered that requirement, because the catalyst, has lowered that requirement, more particles are going to have the energy that they need to react. So a catalyst doesn't increase the frequency of collisions, and it doesn't give the particles energy. It just lowers the energy needed for the particles to undertake a successful reaction. It's similar to the idea of a pass mark in a test. If the pass mark was set at 70%, say 20 out of 30 students have passed. If I wanted more students to pass that test, but I didn't want them to resit it, and I didn't want to just alter their marks, what I could do is I could lower that pass mark. If I lower that pass mark to just 60%, then more students will have the required percentage that they need to pass, and my pass mark might go up then to 25 out of 30 students passing in my class. It's the exact same here for a catalyst. It doesn't give the particles more energy. All it does is lowers that pass mark. It lowers the amount of energy needed for the reaction, which means more particles will have the energy needed and more particles can react. In that way, a catalyst is increasing the rate of the reaction. As well as looking at the effect that these things are going to have on the rate, we need to look at the effect they will have on the amount of product being made, which can be called the yield. So we saw that when we increased the surface area of a reaction, that we ended up increasing the rate. But just because you're increasing the speed of the reaction doesn't mean that you're going to increase the amount of product. And simply increasing the surface area is not going to increase the amount of the product that you are making. If you increase the concentration, we saw again that you were increasing the rate, you're making the reaction faster. But in this case, if you're increasing the concentration, you are going to increase the amount of product or the yield. And the reason is because when you're increasing the concentration, if we look back at my diagram, if you're increasing the concentration, you're starting with more reactants. And if you're starting with more reactants, you're going to make more products. When we looked at surface area, I've got the same amount of carbon in both reactants. In this case, I've got carbon in a large lump, and in this case, I've got carbon in small pieces. But overall, let's just say I've got 20 grams of carbon in each reaction. I'm not changing the amount of carbon, I'm just cutting it up into small pieces. If you've got the same amount in each reaction, then you're going to form the same amount of product. But with concentration, I don't have the same amount in each reaction. I've got more. If I'm increasing the concentration, yes, I'm increasing the rate, but I can also increase the amount of product formed. With the gases, again, when I was looking at pressure, I'm going from low pressure to high pressure, but I'm not increasing the amount of particles I've got. I've got 3 orange dots and 3 blue dots. I've still got 3 orange dots, 3 blue dots. Yes, the reaction will be faster, but I'm not going to increase the amount of product formed. So if I increase the pressure, I'm going to increase the rate, but I'm going to have no effect on the yield. Temperature, again, we saw that it would increase the rate, but again, it's going to have no effect. It'd be similar to if you were baking a cake. If you wanted to increase the amount of cake that you were making, the only thing that's going to increase the amount of cake you're making is if you increase the amount of the ingredients that you use at the start. Simply cooking the cake at a higher temperature, that's not going to increase the amount of cake that you are making. It's just going to cook it quicker. So they will all increase the rate, but it's only the concentration that can actually increase the amount of product formed. Catalyst is no exception to that. Again, it can increase the rate, but a catalyst will have no effect on the amount of product formed. Only increasing concentration can affect the amount of product that you are forming. If we go back to the exam questions, we can have a look at some of these. So this is the graph that I drew earlier, but the next part of that question was, on the graph above, sketch what you would expect to see if you did the same experiment again, but with powdered zinc. So you started off using large pieces of zinc, granulated zinc, and then you used powdered zinc. Powdered zinc, which is small pieces, you've got small pieces, you have got a larger surface area. So if I'm increasing the surface area, what's going to happen to the rate of my reaction? Well, if I increase the surface area, I'm going to have more frequent collisions and I'm going to have a faster rate. So when I'm drawing my line here, I need to show that it's faster, which means I need to show that it's steeper. So I'm going to start here at 0, but I need to show that it's faster. So I'm going to make it really, I'm using my glittery pen. I'm going to make it steeper. But although I'm making it steeper, increasing the surface area doesn't increase the amount of products that you are forming, and overall, your graph should level off at the same place. So I need to draw it steeper to show that the reaction is faster, but it needs to level off at the same place to show that I'm not making more product by simply increasing the surface area. And there's another example, here, of one of these types of questions. It says, during any reaction, reactants are used up, the rate will decrease. Why does the rate decrease? So if you're using all of the particles up, what you are doing is you are decreasing the concentration of the reactants. That will just happen naturally during a reaction. You'll decrease the concentration of reactants as they react to form products. If you're decreasing the concentration of the reactants, you're going to get less frequent collisions, and that will slow the rate right down. Make sure you don't say less collisions, make sure you say less frequent to get the mark. This next question relates to a catalyst. We saw that catalysts do not change during a chemical reaction. If the catalyst isn't changing, then you would expect the mass to stay the same, and the graph that shows the mass staying the same is graph C. This is another question where they want you to draw a line on a graph, and this time it wants you to sketch a line to show what you would expect to see if you used a higher temperature. So if I go back up to my graph, I need to show what I would see if it was at a higher temperature. Higher temperature means a faster reaction, which will mean a steeper line, but again, it's going to level off at the same place. Just because you're using a higher temperature doesn't mean you're going to make more product. So I'm going to be drawing a steeper line, but I'm going to be leveling it off at the same place. A similar question asks you about the catalyst. It says you add a catalyst to that reaction, and it wants you to tick the correct box. Change in final volume of hydrogen. So does a catalyst increase the amount of product? The answer is no. Okay, a catalyst will increase the rate, but only an increase in concentration can change the amount of product. So I'm going to have no change. So my answer is going to be B or C. And then how does the mass of a catalyst change? It doesn't. So I need no change and no change. So the answer is going to be C. No change in the amount of product formed and no change in the mass of a catalyst. This is another similar style question. You're told that the original experiment, which is on this page above, you use 4 centimeters of magnesium, but then you repeat it using 1.5. So you're going to use less magnesium. If you're using less magnesium, if you're using less reactants, then you're going to expect the rate to be slower because there's going to be less frequent collisions if you've got less particles in there. But also if you're using less magnesium at the start, then you'd expect to be making less products. If 4 centimeters of magnesium ribbon is producing 40 centimeters cubed of hydrogen, then 1.5 centimeters of magnesium ribbon should be producing 15 centimeters cubed of hydrogen. So when I'm drawing this, I need to draw it less steep to show it's slower, and I need to draw it leveling off at 15. So it's less steep to show it's slower, and it's leveling off at 15. I'm making less product because I'm starting with less reactants. Just look at one more question. This is a 6 mark. They give you a reaction and they want you to describe an investigation that would allow you to see the effect of the size of calcium carbonate on the rate of this reaction. So in one experiment, you're going to use large marble chips, and in the other, you're going to use small marble chips. And you have to describe how you would measure the rate of these reactions, and you would just have to describe the effect that changing the size of the surface area is going to have on the rate. So when you're describing the investigation, you need to say what you're going to keep the same and what you're going to measure. You need to say what the control, you need to give at least one control, and you need to say what you're going to measure in the reaction, and then you need to describe the reasons for this change in rate. Have a go, just jot down a few bullet points of things that you might say if you were given this 6 mark question. Try and use some of the key phrases that we've gone through, and I'll put the answer up now. So I've written out an answer here. You're using different sized pieces of marble chips, but you do need to use the same amount. So if you were going to use, say, 20 grams, you would do that for both. 20 grams of large marble chips, 20 grams of small marble chips. So to make sure you're doing that accurately, I'm going to use a mass balance to ensure I'm using the same mass of marble chips. I'm then reacting those marble chips with hydrochloric acid, and I want to make sure I'm using the same volume and concentration of hydrochloric acid to make sure it's a fair test. So they're the controls. I've mentioned 2 different controls, as well as the equipment I would use. I then need to say how I'm going to measure. You can see that you're producing carbon dioxide. Carbon dioxide is a gas, so you're going to record the amount of gas being produced and how quickly it's being produced. I've used a gas syringe and a stopwatch so I can record the volume of CO2 produced over time. You could also say that you used a mass balance and you recorded the change in mass over time. But again, I'm saying, giving my equipment, gas syringe, and I'm mentioning time. So I get 4 marks for just saying all of that. Then I'm going to describe the effect. I would expect that the small chips give me a faster reaction as they have a larger surface area. And because they have a larger surface area, you're going to have more frequent collisions. So that answer there would get all 4 marks. These type of questions, 6-mark questions on rates, are quite common. You can often be asked to explain in terms of particle collisions why a reaction is faster or slower. If you are asked that, especially if you're asked to describe an investigation, make sure you're giving controls. What do you use to make sure it's a fair test? Mention the equipment that you're using, so mass balance, gas syringe, stopwatch, thermometer if you were looking at temperature, so just mention basic equipment. Mention what you are measuring. So in this case, you are measuring the gas produced, the volume, and you're using a stopwatch to record the time. So say what you're measuring, and then you're going to explain that in terms of particle collisions, and you're always going to say more frequent collisions, not more collisions. That's your key word.